Hi, in today's video I'm going to go over oxidation states and how to calculate the oxidation states of atoms in a compound. So to calculate the oxidation state, treat all bonds as purely ionic. So let me stop there for a sec. When you calculate formal charge, which is another number that can be assigned to an atom, all the bonds are treated as purely covalent. So if you have, a bond between carbon and hydrogen, they each get one electron from that bond. In oxidation state, if I have carbon and hydrogen, carbon is the more electronegative atom, so it gets both of the electrons go to carbon. So continuing the rules, the electrons in bond are assigned to the more electronegative atom. Now you may say with carbon and hydrogen, we always treat them as virtually identical with electronegativity, right? Carbon and hydrogen together is always nonpolar. There is a slight difference in their electronegativity though, so for the purposes of oxidation state, we consider that slight difference. So everything's assigned to carbon. The only time you'll split a bond and say give one electron to one atom and another electron to another atom is if it's the same two atoms. That's the only time you're going to split the bond, because then their electronegativities are identical because they are the same atom. Okay, so we've assigned all the electrons in a bond to the more electronegative atom. Now you subtract the number of assigned electrons from the number of valence electrons. Right, with formal charge, it's the same thing. Subtract assigned electrons from valence electrons. So identical rules here. The difference is how you assign those electrons. So I'm going to go through a few examples here. First one is methane. Carbon is the more electronegative atom, so all of the electrons from those bonds are assigned to carbon. So for carbon, it's going to be 4 valence electrons minus 8 assigned electrons, 2 electrons in each of those 4 bonds, will give carbon a -4 oxidation number. Hydrogens, each hydrogen has 1 valence electron, gets assigned 0 electrons, so it has +1. Right, each of those hydrogens have a +1 oxidation state. Let's do formaldehyde. So a double bond in this one. Now we've got oxygen, carbon, and hydrogen. Oxygen. When you have a double bond, think of it as 2 single bonds. There's 4 electrons within that double bond. Oxygen also has the 2 lone pairs. So assigning the oxidation state of oxygen, there are 6 valence electrons in oxygen, and it gets all 8 of those assigned electrons, the 2 lone pairs and all 4 from the double bond, to give an oxidation number of -2. Carbon has 4 valence electrons. It gets none of the electrons from the carbon to oxygen double bond, but it gets all 4 of the electrons from the 2 carbon to hydrogen bond. Right, 2 electrons in each of those bonds, so 4 total. So it's 4 minus 4 to give 0 as the oxidation number. Then hydrogen, again, has 1 valence electron, minus 0 assigned to give plus 1. Now see if you notice a pattern here. The sum of the oxidation numbers always add up to the overall charge of the compound, right? Both of these are neutral. I have here minus 4 plus 4 times plus 1, right? There's 4 hydrogens, each have plus 1 charge to give 0. For formaldehyde, I have negative 2, which is the oxygen, plus 0 for the carbon, plus 2 hydrogens at a plus 1 charge to give 0. So what you can do is, knowing that it always adds up to the charge of the compound, you can use the oxidation numbers that you know to determine an unknown oxidation number, say with a metal, where they can have a number of different oxidation states depending on what they're bonded to. So in this example, KMnO4, right? This is really an ionic bond between potassium and permanganate. So we know potassium's oxidation number is plus 1 because oxidation number is always equal to the overall charge. The overall charge is plus 1 and there's only 1 atom, so it has to be plus 1. Oxygen is going to be minus 2. Fluorine is the only atom more electronegative than oxygen. So oxygen's oxidation number is almost always minus 2, unless it's bonded to a fluorine or in a peroxide. And I'll do that as the next example to show you why it's not minus 2 in a peroxide. But otherwise, if you ever encounter oxygen and it's not in a peroxide or bonded to fluorine, it'll always be minus 2. So now the overall charge of the permanganate is minus 1. So if I do manganese plus 4 times negative 2 equals minus 1, I get manganese minus 8 equals minus 1, so manganese is plus 7 oxidation state. That's the only way we can calculate it, unless we either know the structure of the permanganate and draw out the structure and count the bonds and assign the electrons, or this is an easier way to do it, knowing that oxygen is going to be minus 2 here. So the last example I want to go through with you is going to be a peroxide. So this is hydrogen peroxide. First off, the oxidation number of the hydrogen, both of them, are going to be 1 minus 0 to give positive 1. That's also a thing you can pretty much always count on. Hydrogen is almost always going to have a positive 1 oxidation state. If you have lithium hydride, where hydrogen is more electronegative, H is going to be 0 minus 1 to give you negative 1. But you can also figure this out because it's an ion, lithium plus H minus. But usually hydrogen will be plus 1. The oxygens now. The oxygen has 2 lone pairs plus the 2 electrons from the oxygen-hydrogen bond right there. So that's 6. Then this bond here, it's between 2 oxygen atoms which have identical electronegativities, so each oxygen gets 1 of the 2 electrons in the bond. So that means it's 6 valence electrons minus 7 assigned to give minus 1, not minus 2. And if we add these all up again, 2 times plus 1 plus 2 times minus 1 equals 0. So this is how you calculate the oxidation numbers of any atom in a compound. Just assign the electrons from the bonds in the lone pairs to the more electronegative atom, and then subtract that number of assigned electrons from the number of valence electrons.